All right, let's talk a little bit about the harmonic series. So this is the series that we talked about at the very beginning of this, the very first exercise, where you're just adding up 1/2, 1/3, 1/4, 1/5, all the way on to infinity. Does that converge or diverge? And for the exercise, I said, I think maybe it converges, because it kind of seems like the parts are getting smaller and smaller. Eventually it's probably going to, sort of level off and hit some particular limit. Turns out that's not actually true, and I'm going to prove it to you right now. So what is this series? I'm going to write out a whole bunch of the terms and then show you, I guess, one way of thinking about it. So here's what I'm going to do. I'm going to group off a bunch of these. I'm going to group 1/3 and 1/4 together. I'm going to group 1/5 to 1/8 together. I didn't write them all out, but from 1/9 all the way up to 1/16, I'm going to group all those together. And then 1/17 to 1/32, I'm going to group those together. And what do I notice happens here? Well, this original top line that I have here, it's going to be greater than or equal to this thing. So I have 1/3 plus 1/4, and if I add those two things together, I'm going to get something that's actually greater than 1/2, because 1/3 is greater than 1/4, and if I do 1/4 plus 1/4, that's 1/2. So if I put a 1/2 down here, that's actually less than what I'd be getting for the series up above. Similarly, 1/7, 1/6, and 1/5 are all greater than 1/8. But if I add up four things that are greater than or equal to 1/8, I'm going to get something that's greater than or equal to 1/2. So this is also going to give me a 1/2. This is 8 things here, and each one is greater than or equal to 1/16. So that's going to give me another 1/2. And here I've got 16 things that are greater than or equal to 1/32. That's going to give me another 1/2. And I can keep doing that. So what I'm doing here is I'm sectioning it all off. And, when I add up these two, I get, I guess, 3 halves. When I add up these 3, I get 2. When I add up these 4, I get 5 halves. And this, because I keep adding up 1/2, 1/2, 1/2, that's going to go off to infinity. And in particular, I can say the following. If I take the sum of the first 2 to the n entries, so here 32 is like 2 to the 5th, that's going to be greater than n plus 2 divided by 2. And let's see, does that make sense? If I add up all of these, that's going to be 7/2. So 2 to the 5th. If I add 2 to 5, I get 7, and my fraction 2 is on the bottom. And this, by the way, is the same thing as n/2 plus 1. So as n goes to infinity, this s/2 to the n also goes to infinity, because n goes to infinity. And if you divide infinity by 2, you're still getting infinitely large. So the harmonic series diverges, which is one of the mathematical things that I distinctly remember learning and thinking that it was so counterintuitive. Like, I really thought that series would converge, and it turns out it doesn't. And it kind of blew my mind. Our next theorem basically says that if a series converges, then the limit as n goes to infinity of a sub n, this sequence that we're using to build our series off of has to have a limit of 0. And I'm going to prove it to you. Why is that? So let's look at our partial sums. That's a sub 1 plus a sub 2 all the way up to a sub n. And if I look at my partial sum s sub n minus 1, that's adding up a sub 1 plus a sub 2 all the way up to a sub n minus 1. And if I subtracted s sub n minus s sub n minus 1, I would end up getting most things would cancel out except for this a sub n on the end, right? Because all these terms up to that point, I guess I could have put in here, the entry before this is a plus a sub n minus 1 plus a sub n. So what can I do with that? Well, what if I took the limit as n goes to infinity of all of these things? The limit as n goes to infinity of a sub n. That's going to be the limit as n goes to infinity of s sub n minus the limit as n goes to infinity of s sub n minus 1. And the thing is, this right here, the limit as n goes to infinity of s sub n, well, that's the limit as n goes to infinity of sum I equals 1 to n of a sub n. We know that that series converges. That's what we were given. So if that series converges, it has to have a limit, and we'll call that s. So we know that series converges to s. So that means that this thing right here is s. But if I'm taking the limit as n goes to n goes to infinity of s sub n minus 1, that's just this exact same series, but I'm leaving off one term. And as n goes to infinity, it doesn't matter if you leave off one term. If you go to infinity, you keep going. So this one is also going to converge to s. And s minus s is 0. So we're left with the limit as n goes to infinity of a sub n is equal to 0, which la-di-da is exactly what we were trying to prove. Check it out. Warning, just a quick warning, if your limit of that sequence a sub n goes to 0, you cannot conclude that the series converges. What's a counterexample? Well, we just did one at the top of the page, you big goofball. It's the harmonic series. So the harmonic series does, in fact, each of these terms is getting smaller and smaller. Like the limit as n goes to infinity of 1 over n does, in fact, equal 0, but that series doesn't converge. So just because those terms go to 0 does not tell us that the series converges, but it's useful because if those terms in that series a sub n don't converge to 0, then we're guaranteed that the series diverges. And this is called the test for divergence. So the test for divergence says if the limit as n goes to infinity of your sequence a sub n does not exist or is non-zero, then the series sum to infinity of a sub n has to diverge. Theorem 4.3 is something not necessarily connected to the stuff above, but is pretty believable. If you have two series that converge, this one and that one, to A and B, and you have any constant C, then if you make a series where you take all of your entries of your A sub n sequence and you multiply them by C, you're just going to still converge, but you're just going to converge to C times A. And the idea here is you can basically factor out the C because you're just adding up a whole bunch of things. And the C will be on the outside, and the stuff on the inside on the parentheses is just exactly this original sequence A sub n. Similarly, if you have the sequence where you're adding up all of your A terms and all your B terms, that's going to converge to either A plus or minus B. Again, it makes sense if you just took all the A's and you group them together and all the B's and group them together, you just get the A and the B. And that's where we're going to stop for now.